So I'm going to start that over again. Apparently I was muted. Oops, sorry. Welcome to Chapter 1, Section 1, Mathematics and Problem Solving. All right, so again, we're going to talk about, to begin with, this guy, George Polya. He was a big deal mathematician who was all about math education. That was his focus, particularly problem solving. His first book was published in not his first, but he published a really important book called How to Solve It in 1945. He's got this 4-step problem solving process that then was important and really new. And when you see it in a second, you're going to go, huh, really? Okay, but it was all about being systematic in your approach to problem solving with kids. So these 4 steps: understand the problem, devise a plan, carry out the plan, and then review. Now, this to you is not earth-shattering, I'm sure. However, then it was, because that's not how it was taught. However, since then, that's how everybody's been taught. So everybody now thinks well, yeah. So we're going to work through his 4 steps. First, understanding the problem is really important. So you can ask different questions to yourself or to who you're working with to help you understand a problem. So could we say the problem in our own words? Could we restate it? What are you looking for? What do you not know? And a lot of times you have to say, what do you know? What do you don't know? What information do you know based on what you're given? And is there extra information floating around that you don't need? Because a lot of times in problem solving, think about what happens in daily life. There's information that you have that isn't relevant, and that happens with all kinds of problems. Then there are all kinds of strategies that you can use to devise a plan. There are 9 in here. Okay, look for a pattern, similar problems, simplify, make a table, sub-goal, diagram, guess and check, work backwards. We're going to talk about all these a little further in depth in a second. Then in step 3, you choose your strategy. And here's the thing, you may choose a strategy, try it out, and have to go again and pick something else. Not every strategy fits every problem. Sometimes you try something, doesn't work out, you try again. But you pick one to start. What's the worst thing that can happen? Then you make sure you understand the problem really clearly and that the numbers you have are accurate. You work through and you check, and you try to record as you go, right? Then your last step is to sort of go okay, this is the answer I found. Does this actually make sense in the problem? Does my math work? Could I have done it a different way, or do I need to? Because maybe this doesn't, my answer is, I got an answer, but it doesn't make any sense. And will what I learned here help me to solve other kinds of problems? That would be great, right? Okay, so there are all different kinds of problem-solving strategies. One of them is to look for a pattern. And we're going to look for a pattern in a really important problem. This is called Gauss's problem. Gauss was another super famous mathematician from quite a while ago. And this is his most famous work. So if you think about natural numbers are numbers you count on your fingers. 1, 2, 3, 4, and on. Somebody said to him, how do you find the sum of the first 100 natural numbers? 1 plus 2 plus 3 plus 4, all the way up to 100. And he thought well, I could add these all together, but I'm going to be here a while, right? And he didn't have a spreadsheet, and he didn't have a calculator, and he thought eek. So ask yourself, is there another way to do this? Maybe there's another way to write the sum. Maybe there's a formula. Or how do you know, and if you do find a formula, how do you know it works every time? Well, there is a formula. But pause for a second and see if you can work through finding a way to sum those numbers efficiently. All right, so hopefully you thought about that. I'm gonna scroll my page down a little bit. So we're adding the numbers 1 all the way up to 100. One of the things you can think about here is taking these numbers and making little rainbows. What if I added 1 plus 100? What would I get? I'd get 101, right? What if I made another little rainbow here? What if I added 2 plus 99? What do I get? I get 101. What about 3 plus 98? 101. 4 plus 97? 101. Interesting. Now it's just a matter of like, how many 101s do I need to add together? And that's way easier than adding all these different numbers, isn't it? So the first thing I do when I solve this kind of problem where I'm summing a series of numbers, this is called a sum of a series, okay, is I add the first number plus the last. Okay, so in this case, that's going to be 101. All right. I imagine it like, you know, the paper paint butterflies you made in school, you took it, you folded it in half, you mushed them together, right? It's like I took this series of numbers here and I folded it down the middle. But here's the thing. I don't know how many 101s I have. So this is the sum of the first and last. Now I need to find the number of elements. That's how many 101s. Okay? Actually, it's not how many 101s. That's me misspeaking. The number of elements is the number of items on this list. So like, how many things are there from 1 to 100? Well, I have to use the number 1. Okay, the way I actually figure this out, it's really 100. You think about it, right? The way you figure out the number of elements is you do last minus first. Okay, so in this case, it would be 100 minus 1. And then we're always, always, always going to add 1 to that. So 100 minus 1, is 99 plus 1 is 100. There's 100 elements. Now here's the thing. We always add this 1 at the end. It's the last thing we do here to find the number of elements. Because what it does is it accounts for where you folded your paper to make the butterfly. There's somebody in there maybe without a partner. And we have to account for that. Okay? Pardon me. So now we are almost there. So we have first plus last, that's 101. We're going to multiply it by the number of elements. That's 100. But here's the thing. That 101 is made up of 2 elements, isn't it? It's made up of a 1 and a 100, or a 2 and a 99. So I don't want 100 of these. I want half as many. I'm going to divide this whole thing by 2. So 101 times 100 is 10,100. I divide that by 2. Well, 10,000 divided by 2 is 5,000, right? 100 divided by 2 is 50. I get 5,050. So if I were to add up all the numbers from 1 to 100, the sum is 5,050. All right, so this was pretty weird, right? Let's try another one. The thing is once you've done some of these, and you're going to do some of these, this is one of those things in this class that's going to come up over and over and over again, so sorry. Okay. Once you've done a couple, we can just apply the same process. So in the last one, we started by doing the sum of the first and the last. Well, 147 plus 36. Oh, gosh, it would help if I wrote the number in the correct order. That's a 63. Okay. 147 plus 36 is going to get me 183. Okay, so the first plus the last is 183. All right, now I need to do 147 last minus first minus 36, which is 111. At the end of that, I'm going to add 1 for the fold, right? So that's going to be 112. Divide the whole thing by 2. You can multiply those numbers. Multiply 183 times 112. I get 20,496. I'm going to divide that by 2. Okay. Well, and I can divide it in pieces. So 20,000 divided by 2 is 10,000. 400 divided by 2 is 200. And 96 divided by 2 is 48. There's my answer. That's the sum of those numbers. There is one more not here in the notes that I want to try. I'm going to extend the page a little bit. I just want to show you a different example. So say I wanted to add 3 plus 5 plus 7 plus 9 all the way up to 99. Okay? This is a little different, this example, because I'm not counting by ones anymore, right? I'm counting by twos. So we're going to do one thing that's different. We are going to start the same way, sum of the first and the last. So 3, I want a different color. 3 plus 99 gets me 102. That's a 2. It's still not look like a 2. All right, and we're still going to find the difference. Last minus first. So 99 minus 3 is 96. Before we add the 1, we have to do something else. We have to account for the fact that we're counting by twos. So we're going to divide this 96 by 2. If you were counting by 3, you would divide by 3. If you were counting by 4, you'd divide by 4. If you were counting by 5, you'd divide by 5. At this spot, this is what you're counting by, okay? So 96 divided by 2 is 48. Now you're going to add 1. Always that's the last thing you do, so 49. Okay? So now I have my last plus first, my number of elements, times my sum. But remember, I'm still using two numbers summed together for this 102, so I still have to divide by 2 at the end. Okay? So 102 times 49 is 4,998. I have to divide that by 2. 4,998 divided by 2. Let's see. 4,000 divided by 2 is 2,000. 9,000 divided by 2 is like 450. 98 divided by 2 is 49. So 450 plus 49 is 499. All right, so that's my sum. So now you see what to do when you're adding, when you're summing a series of numbers counting by 1 or by counting by something else, okay? You'll see this in the homework. All right. Oh, and I got ahead of myself. I had a slide for that. All right. Let's look at another one. This is solve a simpler case. Oh, sorry, that was solve a related problem, right? So that was example strategy number 2. So we solved something similar to what we did the first time. Strategy number 3 is look at a similar case. So, or simpler case. So imagine you have triangular crackers. Yum. Each side is 1 inch long. Okay, so if you imagine my cracker, here it is. Each side is 1 inch. Okay. I have 100 crackers stacked in a row. I want to know the perimeter. Well, I don't know that I want to draw 100 crackers, but I can start with something smaller. Like if I had 1 cracker, let's make this the number of crackers. And let's make this the perimeter. Let's keep track. So if I have 1 cracker, it's got perimeter is 3. 1, you add the sides together, right? Great. So if I have 2 crackers, what does that picture look like? Well, let's draw it. So 1, and you can see they stack them side by side. They flip, right? Well, the perimeter is 1, 2, 3, 4. Well, that's weird. What happened? What you can see in here is that third side, they became an inside, right? So this is 2 sides right here smushed together. All right, well, if I have 3 crackers, what happens? Let's see. 1, 2, 3. So I got 1, 2, 3, 4, 5. Huh. But let's see what happens. That second cracker now only has 1 side on the outside, right? There's 2 ends from the original cracker. and 2 ends from the new cracker, right? And then this guy only gets one side showing. So let's see what happens if we have 4 crackers. Well, 1, 2, 3, 4. Let's see, 1, 2, 3, 4, 5, 6. Huh. But you can see what happened here, right? Let's change colors again. Ends, ends, and these guys in the middle, they just only get one side. Okay, so now are you starting to see a pattern? Can you use that pattern to help you get to 100 crackers? Well, so I see that 1 cracker plus 2 is a perimeter of 3. 2 crackers plus 2 is a perimeter of 4. 3 crackers plus 2 is a perimeter of 5. Plus 2, perimeter of 6. Huh. Well, what if I had 100 crackers? The pattern is going to hold. I'm just adding crackers, really. It's going to have a perimeter of 102. There are lots of ways to solve this problem with pictures or with other things. However you did it, it's fine. Okay? So there's a couple slides here about working through this. I usually just do it in that same slide. But it's make it, so in this case, it's make a simpler case, but it's also making a table. Didn't we make a table to solve that? So it's also making a table. We see the pattern. All right. In problem solving strategy number 5, we identify a sub-goal. Sometimes when you're solving a problem, it's useful to go oh, okay, what is this one piece I need? It's like when we did the Uidoko puzzle in the last video, right? I had to figure out what all the numbers were before I could solve it. That's a sub-goal, right? I need to solve this thing before I can do that thing. Another kind of puzzle where this is the case are magic squares, and kids love magic squares. Like if you work with kids at all, school age ones, you can do these with them tomorrow. They'd be all over it. Okay. We need to solve a sub-goal here to be able to make a magic square work. Okay. You know, we can guess and check for days, but there's actually a smarter way to do it. So here's our magic square. In a magic square, there's 9 numbers. In this case, we're going to use 1 through 9. And what we do is we put those numbers in here so that the sum in each row and column is the same and diagonal. So magic squares are a little different than that Uidoku or Sudoku puzzle, but still. Now here's the thing. What's our sub-goal? It would be really helpful to know something. What would be helpful to know? It would be super helpful, I think, to know what the sum has to be, wouldn't it? Huh. Because if I can figure that out, I can make different combinations of that sum and put them in the rows and columns, and I'd be off. Okay? So, well, I have the numbers 1 through 9. So if I add them all together, Gauss, isn't that what that was about? In this case, you may not need to use that formula because you can add the numbers 1 through 9, right? But, so we can use the formula just because we just learned it, right? So first plus last, 9 plus 1 is 10, right? First minus last, I'm counting by 1, so 9 minus 1 is 8, plus 1 is 9. That whole thing divided by 2. 9 times 10 is 90. 90 divided by 2 is 45. Ooh, and I wrote 9 for some reason because I was saying the word 9. Okay, so 45. So the sum in each row and column is not going to be 45, but here's the thing. There's 3 rows at any given moment. So 45 divided by 3 is 15. So, ooh, sorry. Each row and column needs to make 15. Ah, that helps. So now we just need to think about ways to make 15. So think about the numbers 1 through 9. Well, let's see. I could add 1 plus 9 is 10. Oh, that should look like a 9. Plus 5, that would be 15, right? And maybe 9. Let's see, can I use 9 again? 9 and 2 and 4, right? That's another 15. And can I use 9 again? Let's see, 9 And 6 would be 15 plus 3. That would give me 8. All right, so there's a whole bunch of ways to make 15. Now you just make those groups together. Here's the thing. This is in your textbook on page 8 and 9. You either have your textbook or you're using MyMathLab to do it. Either of those is fine. But you can go see the answer here. I'm not going to put it in here. I want you to figure it out. There's lots of ways to solve this. You try yours, okay? All right, next, we can make a diagram. So pretend there's an elevator, and it's stopped in the middle floor of a building. Goes up 4 floors, stops again, goes down 6, stops, moves up 10, and stops again. It's 3 floors from the top. How many floors does the building have? Well, I think it would be good to draw a picture, right? So let's draw the building. So here's my building. The elevator is here in the middle. I don't know where that is exactly, but I know it's there. So it's going to go from here up 4. So that's 4. And then it's going to move down 6. All right, so let's see. If that's 4 and the whole way down is 6, this would be 2, right? It's 2 below now. And then it's going to go up 10 floors and stop. So it's going to go up 10. So this is 6, 7, 8, 9, 10. That's 4 more. All right. Now it's 3 floors from the top. Here's the top. So let's see. 3 and 4 is 7, 8, 9, 10, 11. So there's 11 floors up there. So if that's the top half, that means there's 11 floors down there. But here we were at the middle, right? So we got 1 more. So altogether, 23 floors. Could you have done this another way? For sure. I have seen kids do this with a chart. I have seen kids make a model. I have seen kids do all kinds of different things. But that means that that's okay. There's lots of different ways to do this. It's really important that when you see that in a classroom, that you say, oh, look, Joe had a different way to do it. Why don't you show us, Joe? And then everybody learns from his strategy, and maybe they'll use it some other time. All right, so next, guess and check. Here's the thing. This is trial and error. You make a guess. You see if it's correct. You try something else. You try to use what you learn from your first guess to make a better second guess, and so on. One of the things that's very clear is that lower elementary students, their first instinct, particularly in those grades, is guess and check. As kids get older, they use it less because they have more strategies in their tool belt, as it were. But for younger kids, part of what you do with them is you teach them to guess and check effectively. Okay, so the better you do at that and say like, oh, okay, so that good guess first time, how can you use that to help you the second time? Great. All right, this is a guess and check problem. So what we want to do in this problem is find the digits that can be substituted into each of these letters to make the statement true. So, let's see. I know this is an S and this is an S. So I'm going to start there, right? Because that's the only weird thing in this puzzle. Because I'm going to add S and F and get a 2-digit number. Well, that means that this has got to be a 1. I can't figure out how I would add 2 numbers and get more than 20. So let's make them a 1. All right. Well, 1 plus something, I'm going to get a 1 to carry here. There's only one way to do that. That's got to be a 9. And that'll make a 10. So 1, 9, that's a 10. From here, I'm clearly not carrying anything over. It doesn't say that. So I just have to add 2 numbers that's just going to add up to something I don't have to carry. And then there's lots of answers here. So like U might be 2. So that makes 2 and 2, and I is 4. Maybe N is, let's see, can't be 4, can't be 2, can't be 1, can be 3. 3 and 3 would make 6. Sure, and we're there. Could you have swapped these 2 columns? For sure, totally works. One of the games that you can play with younger kids that's a guess and check game is called Broken Calculator. What you do is you say to them, I want you to make me the number 406, but the button on your calculator is broken. How do you do it? And they have to guess their way through. And you know, I actually have played this with kids of all sorts of grades in elementary school, because when they get older, you say to them, I need to make 1,306. The 1 key, the 3 key, the addition key, and the multiplication key are broken, and you just mess with them. But it does force them to use guess and check to work through. All right, numbers. Oh, this is the rules for Broken Calculator. I knew they were here somewhere. All right. And then the last strategy is to work backward. We all do this at some point, right? One example where we work backward is a multiple choice test. We stop and we go like, oh, I don't know the answer to this at all. Well, let's see, which one couldn't it be? Or if these are the answers, which ones could I plug into the problem and have work out? Okay, we eliminate the options that don't make sense and work backward to see what's correct. Think about other examples of times you work backwards. Okay. So this is, there's one more. The last one is to write an equation. You do this in algebra for sure, but a lot of times kids in younger grades write missing number problems, right? Those are equations. They're just not using letters. So 14 plus something gets me 17. Well, I know in here goes 3, but this is an equation. Anything you set up with an operation and an equal sign, whether you use a variable or a picture or something else, those are writing equations. And kids can translate their words into equations. Great practice for them. All right, so we have been through all the problem-solving strategies. This is the end of this recording. From here, you are going to work on the assignment in MyMathLab, which is 1.1. You are also going to work on the written assignment and the discussion for this section. You will see them all listed in Canvas. Just work your way through. As you have problems, I'm happy to help. Just let me know, and I will see you on the video for 1.2.